Hello grade 11, welcome. In this video, you will learn more about magma, its composition, types, and how magma is formed. Tara! Our discussion will focus on the learning competency, describe how magma is formed. At the end of the lesson, you should be able to 1. Describe the chemical composition of magma. 2. Differentiate the three types of magma. And number 3. Identify the processes on how magma forms. Volcanic activity is one of the most powerful forces in nature. Volcanoes vary in shapes, sizes, and eruption types. Violent eruptions occur when pyroclastic material, a mixture of magma, rocks, ash, and hot gases, is exploded upward by pressure caused by underground gases and magma. Now, what is magma? Magma is a molten and semi-molten rock mixture found under the surface of the earth. When magma is ejected by a volcano or other vent, the material is called lava. Magma that has cooled into a solid is called igneous rock. Magma is extremely hot, between 700 degrees and 1300 degrees Celsius. This heat makes magma a very fluid and dynamic substance, able to create new landforms and engage physical and chemical transformations in a variety of different environments. Magmas can vary widely in composition, but in general, they are made up of only 8 elements. In order of importance: oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. Oxygen, the most abundant element in magma, comprises a little less than half the total, followed by silicon at just over 1/4 and the remaining elements, as shown in the graph. Now let's discuss magma formation. Earth is divided into 3 general layers. The core is the superheated center, the mantle is the thick middle layer, and the crust is the top layer on which we live. Magma originates in the lower part of the Earth's crust and in the upper portion of the mantle. Differences in temperature, pressure, and structural formations in the mantle and crust cause magma to form in different ways. This picture shows the common sites of magma formation in the upper mantle. The first type of magma formation is the decompression melting. This involves the upward movement of Earth's mostly solid mantle. This hot material rises to an area of lower pressure through the process of convection. Areas of lower pressure always have a lower melting point than areas of high pressure. This reduction in overlying pressure or decompression enables the mantle rock to melt and form magma. Decompression melting often occurs at divergent boundaries where tectonic plates separate. The rifting movement causes the buoyant magma below to rise and fill the space of lower pressure. The rock then cools into new crust. Decompression melting also occurs at mantle plumes. These are columns of hot rock that rise from Earth's high-pressure core to its lower-pressure crust. When located beneath the ocean, these plumes are also known as hotspots. These push magma onto the seafloor and can grow into volcanic islands over millions of years of activity. Magma can also be created when hot liquid rock intrudes into Earth's crust. This is called heat transfer. This happens at convergent boundaries where tectonic plates are crashing together, melting the surrounding rocks into magma. As the denser tectonic plate subducts or sinks below, hot rock from below can intrude into the cooler plate above. This process transfers heat and creates magma. Over millions of years, the magma in this subduction zone can create a series of active volcanoes known as a volcanic arc. Next is flux melting. This occurs when water or other volatile components are added to rock. These compounds cause the rock to melt at lower temperatures. This creates magma in places where it originally maintained a solid structure. Much like heat transfer, flux melting also occurs around the subduction zone. In this case, water overlying the subducting seafloor would lower the melting temperature of the mantle, generating magma that rises to the surface. There are 3 types of magma: the basaltic or mafic magma, the rhyolitic or granitic magma, and the andesitic or intermediate magma. Basaltic or mafic magma forms at the mid-ocean ridges or at hot spots under the ocean crust. This is high in iron and magnesium but is low in silica. Rhyolitic or felsic magma, also known as granitic magma, forms from the partial melting of continental crust and is low in iron and magnesium but high in silica. And we also have the andesitic or intermediate magma. This forms when the magma did not erupt but instead slowly crystallized within the Earth's crust. Magma has a medium silica content. The silica content of a magma determines whether it is viscous or fluid. In composition, basaltic magma is 45 to 55% silica, high in iron, magnesium, calcium, low in potassium and sodium. Andesitic magma is 55 to 65% silica, intermediate in iron, magnesium, calcium, sodium, and potassium, and rhyolitic magma is 65 to 75% silica, low in iron, magnesium, and high in potassium and sodium. A volcano's eruptive style is affected mainly by the gas content of the magma. Let's consider a bottle or can of soda. Opening a bottle of soda after shaking causes the contents to overflow because of the gases dissolved in the liquid. We normally can see bubbles in the soda. However, if we shake the bottle, we can see some of the bubble coming out of the solution. And when the bottle is open, pressure decreases and the escaping gas causes the bottle to overflow. The same thing happens as magma rises towards the Earth's surface. As you can see in the illustration, gases dissolved in magma under pressure come out of solution as magma rises. In this phase, the volume increases. The expanding gases force magma upwards and drive the eruption. Therefore, gas gives magma their explosive character because volume of gas expands as pressure is reduced. The composition of the gases in magma are mostly water with some carbon dioxide and minor amounts of sulfur, chlorine, and fluorine gases. Viscosity also affects the eruptive style of a volcano. Viscosity refers to the resistance of substance to flow. Liquids that flow easily, like water, has a very low viscosity. For example, we have honey, milk, and olive. Honey has a very high viscosity while milk and olive oil has a very low viscosity because it flows easily. Viscosity of magma affects the violence of volcanic eruption. Let's watch this simple demonstration.
Imagine blowing air through a straw into a glass of water. The low viscosity water will bubble readily as the air escapes without much effort.
Now, try doing the same thing again, but this time, replace the water with a milkshake. First, it'll be more challenging to blow air through the mixture. Second, if you succeed, it'll react more vigorously and splatter the milkshake over anyone standing nearby. The higher viscosity milkshake makes it difficult for air to escape, causing the pressure to build up and producing bigger bubbles.
Viscosity in magma depends primarily on the composition and temperature. Higher silica content magmas have higher viscosity than lower silica content magmas. Viscosity increases with increasing silica concentration in the magma. Lower temperature magmas have a higher viscosity than higher temperature magmas. Thus, basaltic magmas tend to be fairly fluid, but their viscosity is still 10,000 to 100,000 times more viscous than water. Rhyolitic magmas tend to have even higher viscosities ranging between 1 million to 100 million times more viscous than water. And that ends our lesson. Congratulations!